Denticity. It is the number of coordinating or ligating groups present in a ligand. For example, in H2O, Cn negative, NH3 negative, there is only one donor atom. In water, this oxygen has two lone pair of electrons and has a tendency to donate this lone pair of electrons to the central metal atom and to form the coordinate bond. There is only one donor atom, that's why it is called as monodentate ligand or unidentate ligand. Similarly, in Cn negative, nitrogen has a lone pair of electrons to form coordinate bond. In ammonia, again nitrogen has a lone pair of electrons for forming the coordinate bonds with central metal atom. It means in monodentate ligands only one donor atom is present which donates its lone pair to the central metal atom and forms the coordinate bonds. And next is the didentate ligand, in which two donor atoms are linked to the central metal atom. For example, En. En is the abbreviation of ethane 1,2-diamine and its formula is NH2 CH2 CH2 NH2. Here this is one carbon and this is second carbon and the name is ethane 1,2-diamine 1,2-diamine. This is ethane CH2 CH2. And next example of didentate ligand is oxalate ion. Here in ethane 1,2-diamine, two nitrogen atoms which form coordinate bond with the central metal atom. And in oxalate ion, COO negative, COO negative. These two oxygens form coordinate bond with the central metal atom. It means it has two donor atoms in ethane 1,2-diamine as well as in oxalate ion. That's why these are called as didentate ligands. And another example is of glycinate ion, or it abbreviated as GLY, and its formula is CH2 NH2 CH2 NH2 and COO negative. This is the glycinate ion, in which two donor atoms are present. One is oxygen and other one is nitrogen, which forms two coordinate bonds with the central metal atom. And next is terdentate ligand. For example, diene or N2-aminoethyl ethane 1,2-diamine, and its formula is H2N CH2 CH2 NH, which is further linked with two carbons CH2 CH2, then NH2. It has three nitrogen atoms which are donor atoms they form coordinate bond with the central metal atom. And this is the formula of diene. N2, N represents the nitrogen through which the coordinate bond is formed, and here it is the 2 amino group. This is first carbon, this is second carbon, and this group is the 2 amino ethyl group, and this is the ethane 1,2 diamine. And the next is ambidentate ligand. In ambidentate ligand, it is a unidentate ligand which have two or more donor atoms, but only one atom is attached to the central metal atom during the complex formation. It means it has two sides available for forming the coordinate bonds with the central metal atom. For example, NO2, in which when nitrogen is linked with the central metal atom with coordinate bond, and another way when oxygen is linked with the central metal atom. It has two donor atoms, one is oxygen and one is nitrogen, but only one donor atom is attached at a time with the central metal atom, and NO2 has two sides for making the bond coordinate bond with the central metal atom. One is oxygen and other one is nitrogen, and this is called the ambidentate ligand. Other one is SCN, in which sulfur forms the coordinate bond with central metal atom, and another way in which nitrogen forms the bond with central metal atom. It has two donor atoms, one is sulfur and other one is nitrogen, but only one is attached at a time, and these are called as ambidentate ligands. This is chelation. Chelation is a property of the coordination compounds in which a ligand having two or more donor atoms linked to the central metal ion in such a way that they form a ring, and this ring is called chelate ring, and the resulting complex is called metal chelate, and the property shown by the compound is called chelation. For example, this is ethane 1,2 diamine, in which two nitrogens form coordinate bonds with the central metal atom, and they form a ring with this central metal atom, and this ring is called metal chelate ring, and the property shown by this metal chelate is called chelation. And another example is of nickel, in which nickel is forming a ring with this diglyoxime. This is diglyoxime, in which four donor atoms are linked with the nickel, that is central metal atom, through coordinate bonds, and they form two rings around the nickel atom, and this ring formation is called chelate ring, and the property is called chelation. And these chelates are widely used in industry as well as in laboratory. For example, in softening of hard water. in separation of lanthanoids and actinoids, and in detection of some metal ions in qualitative analysis, or in estimation of nickel, magnesium, and copper ions quantitatively. Chelates are used in industries as well as in laboratories. Next is important terms used in coordination compounds. First one is coordination number. Coordination number means number of neighboring atoms attached to the central metal ion. Here in coordination compounds, it is the total number of ligands which are directly linked to the central metal ion. They show the coordination number. Next is the coordination sphere, in which the central metal ion and the ligands which are directly attached to the central metal ion in square brackets represents the coordination sphere. And third one is counter ions. Counter ions are the ions outside the coordination sphere, and these are ionizable ions. And this positive charge is the change number of complex cation. And here in this example, cobalt has a oxidation number of +3, and the oxidation number means charge acquired by the central metal ion. And coordination number in this example is 6, because there are 2 chlorine atoms and 3 and 4 NH3 molecules which are directly linked to the CO, cobalt central ion, and these are in 6. They are in their number is 6. 4 plus 2, 6. Hence the coordination number is 6. And there is only one counter ion, that is Cl negative. And the oxidation number of cobalt is 3 positive. How can you calculate the oxidation number of the central metal ion? Suppose in this example, let the oxidation number of CO is X, plus we have 2Cl and it carries -1 charge, and 4 ammonia groups which carries no charge, and there is 1 chloride ion which is equal to, which is also -1. And the overall charge of the complex is 0. And from here we have -3, which after going to the equal sign it becomes +3, and the charge on the oxidation number on central metal ion is +3. In this way we can calculate the oxidation number of the central metal ion. Next is homoleptic and heteroleptic complexes. Homoleptic complexes are those complexes in which a metal atom is linked to only one type of ligands. For example, in this coordination complex, there are 6 ammonium ions. 6 NH3 ligands are attached to the cobalt central metal ion. It means they are of same type. All the ligands are same. Only one type of ligands are attached in this coordination complex, and this +3 is the charge on the complex. Next is the heteroleptic complexes, in which a metal atom is linked to more than one kind of ligands. For example, in this coordination compound, platinum is attached to NH3 as well as Cl, chloride and NH3. It contains two types of ligands. One is neutral and other one is negative ligand. And this type of coordination complex is called heteroleptic complex. Next is homonuclear complex, in which only one metal atom is present. For example, in this complex, Ag is the only central metal atom which is present. That's why it is called as homonuclear complex. Next is the heteronuclear complex, in which more than one metal atom is present. Like in this, these are two cobalt central metal atoms which are linked to two ethane 1,2-diamine and NH2OH, which forms the bridge between these two CO atoms, cobalt atoms. And these are the counter ions or ionizable ions, SO4 2. And this is example of heteronuclear complexes in which more than one metal atom is present. Here we have two cobalt